And it'll be great to hear from you how we could marry this data we got from MCGM,
Okay.
vaccination, testing, etc., with what probably exists on HMIS. You know, the HMIS.
That's like the health registry database.
Yes.
Yeah. Okay.
And anything else that you would like to guide?
Yeah, that sounds good to me.
Can we start the screen share?
Yeah. So first of all, I think we should introduce Shekhar sir.
Oh, sorry.
Yeah.
Yeah, we can have
Yeah, Shekhar sir, can you please switch on your camera?
Shekhar?
Yes. Switched on. I don't know whether you're able to see me.
Yes, yeah, I see you very clearly.
Okay, very nice. Hello. Hello, Niket. Hello, Professor. Hi, Rashmi. Hi, Anuj. I'm in Bangalore, so I'm joining remotely. I have a dual role. First of all, I'm a student at KCDH. I've just enrolled this January to pursue my PhD. I've done a lot of research in the past with CMU for the last 20 years in various areas, principally with information retrieval, searches, ontologies, knowledge management, that space. And I just wanted to take it to a logical conclusion. At my alma mater, I studied my undergrad at IITB and I met Dr. Professor Ganesh actually. And there was a meeting of basically the ideological mind. So then I thought I'll continue here. So this is what I do as one part of my job. I also am, I head up an institute called Vadvani Institute for Artificial Intelligence. I'm its CEO. And essentially, we are in the space of delivering applied AI solutions to assist the underprivileged and poorest people in India. We are working on over 20 to 22 solutions now. 15 to 16 are in health. The rest are in agriculture and will start in education. Tremendous opportunity. So there's the pure research, and then there's the marketplace, and there's a big gap between the two. And that's where we sit. We necessarily do not do only research. We spend a lot more time on problem definition. So for every one person who's proficient in AI or an AI/ML person or an AI/ML scientist, we almost have 3 to 4 other people who need to do work. This is a discovery because you need to work with the government. You need to define the problem with clarity. You need to sit and work with a much better understanding of the ecosystem. On the implementation side, while the AI/ML is very important, we feel a lot more is resident on adoption. So we exist to make, from our institute perspective, we exist to actually deliver things. So right now I have started my work here with VPD, particularly my measles, and I'm also starting to look at a couple of entities. And we have some specific ideas from my end we've been discussing with the students as well, which actually may be less pure research, a lot more applied, a lot more what we find for problem solving so that it will stick in the marketplace. So that's my background. Thank you again for the opportunity.
Thank you for the intro.
Thanks. If you don't mind, you can keep your camera on because I think it just is creating a feeling as we are all in one place. Anuj, I'd like to.
Yeah, so I'm currently a dual degree student. I did my BTech in mechanical from IIT Bombay, and now currently I'm doing a master's in health informatics under Professor Ganesh. Yeah.
So Anuj has been more of the modeling part, AI modeling, etc. So maybe we can run through some of the findings so far.
Yeah.
Anuj's findings, findings from the rest of the team. Whatever we presented last week, right? And the peek into the data set through our findings, right? So that way.
Beautiful. Yeah, that sounds good.
All synthetic data, right?
Yeah.
Piyush can also present your.
Yeah. So this is the.
You can decide the order. Keep it free flowing.
So this is the data set which we received from our municipality.
And you can maybe enlarge it a bit. Others can see, right, through the Teams. You're able to see the screen?
Yes, clearly.
Yeah.
So, so we got 4 years data, 2019 to 2022, and basically the last year, the previous year has many cases as compared to the previous 3 years. 1,638. So, and the columns, if we talk about here, are more than 200. So they have one pattern in which they can record the complete detail about each and every person. So suppose here they have some which year they have reported case, some ID related thing they have put under this here column, some EPI number they assign to each and every patient.
Oh, that
Big ID.
that year is the calendar year. Okay, okay. I was like,
And-
22-year-olds are getting measles.
So similarly, like here, date of notification, the date,
Yeah.
and the date of notified by whom, and each like very minor details they have reported in their record. So investigated by whom, at what date, verified by whom. Many details are here.
Yeah, that's great. Do you have like an outcome? Do you know if everyone in this data set recovered, or do you know? So like,
Final, you have the final status.
Final status, yeah, final class. So these
oh wow, yeah, there's so much.
so much
stuff.
information.
Yeah. Oh my God, and types
When
of
the blood
symptoms.
test they gave for blood.
Oh,
test,
great.
this
Okay.
report
And they do an IgM test. Great. Great. Okay.
It's clinically compared, basically, as we understand so far, means the clinician thought it was positive, either measles or rubella, and the lab test seems to have not or fallen through or whatever. Right?
Yeah, that's correct. So
Is that what you understand?
so there's these have a WHO definition.
Oh, is it?
And what you've just said is correct. So clinically compatible means like it's one of the 4 C's. Which
Yes,
is
yeah,
like,
correct. That is
yeah.
influenza and
Yeah, so you're familiar. And also fever,
What are the 4? Crop,
cough,
cough.
conjitis, which is like the red eyes. And then there's a C that's for the rash. I don't know what it's even is. And I have to look at it,
Coryza.
but just like the fever, the eyes, and the runny nose.
Yeah, saying something, Shikha?
Coryza, conjunctivitis, cough, and the 4th C is the rash.
Yeah, okay. And so basically like if it fits that definition, and what we find in data, say from Nigeria, is that the accuracy, like what's the word for like the false positive rate for clinically compatible varies a lot region to region and is correlated with like routine immunization, stuff like that.
But it's certainly not
Definitive.
measles or rubella.
No, it could easily be measles or rubella.
Oh,
It's clinically compatible, so it's like symptomatically compatible, but like all of the lab confirmed rubella cases were also symptomatically compatible, and all of the discarded cases were also symptomatically compatible.
but clinically compatible means it was not lab confirmed, right?
Correct. Yeah,
So that means as per lab reports, it's not measles or rubella.
that's correct. Yeah.
so on the based on the clinician assumptions or
Mhm.
Exactly.
And so one that wasn't there that's common is also epidemiologically linked. So if they have the symptoms and they have a known like social linkage to someone who was lab confirmed, then they'll change clinically compatible to epidemiologically linked. And that's like another standard WHO definition. But since like this was a major outbreak, right, probably the clinically compatible rate for measles is pretty predictive of it being measles. And so what we find in data from that we've worked with is that like the accuracy of clinically compatible for how predictive it is that it's actually measles, that varies a lot over time. It varies a lot over space. It is highly dependent on like the outbreak specific epidemiological context. So what we've started doing is building regression models with the discarded cases.
Oh,
So like you can a simple like kind of logistic.
discard would mean it was
negative.
It was lab
Clinician
confirmed
deemed to be
negative. No, lab
Lab.
negative. Yeah.
Oh, but clinically compatible is not lab confirmed negative, is it?
No. Clinically compatible is like they haven't even checked. The lab test did not happen.
Yeah.
Oh, the
And-
lab test did not happen yet.
And then discarded means like it's lab confirmed
Oh.
negative.
Okay.
And so we use the discarded cases quite a bit actually to be able to predictively classify standard ways, logistic regression with like some of these other columns to predictively classify if that row should be counted as measles or not. And so we have like in the back end, when we're doing data processing for our transmission models, we run some classifier standard stuff on these outcomes.
So what you try to do is
Sort the clinically compatible cases into the ones that we think are probably measles based on other covariates. That's so many. Yeah, but like the ones that like matter a lot are like time, because like if there's a lot of measles in the area at that time, that's meaningful. Whether or not they report having a vaccination status, and then also their age is very predictive. So usually we just use those three, like when the case was reported, whether or not they report having been vaccinated in the past, and how old they are. And you can build quite predictive models.
So it looks like we made a mistake then, right? Because we tried building a decision tree on all these classes, the 4 of them, right? 4 classes. I don't know. My understanding of clinical compatible was different earlier. I thought they were actually deemed to be negative, but you're saying they're not yet even tested.
Not even tested, yeah.
And the other input I get here is maybe we should build a model which can help determine which of those clinically compatible cases should probably be subject to a lab test.
Yeah. So that's the sort of thing that we do. We're working with data like you are, like years past. So we don't frame it that way because it's not like real time.
But in real time. So
yeah,
actually,
so you could, yeah.
Could go back to MCGM based on February data and say, well, for March, you may want to consider testing these.
Yeah, and if you can do things like
a monthly basis.
You can do things like, okay, like if you know the age of the patient and you ask them a couple questions about themselves, you can have a probability that you should test or not, right? And there's some people that like the probability that the symptoms are predictive of measles is like close to 1. It's a wasted test. You already know because they're young, they have no vaccine, and lots of people are getting.
They don't have vaccine, yeah.
But there's people where it's very close to like 50%, right? Coin flip. And so those are the people that you would want to say like, well, we should lab confirm this. And in particular, like if you're building one of these models across a population, you can quantify the uncertainty in your estimate of the classification probability, right? And so we use that to say like, this is an area where you need more surveillance. But it's kind of like, the way we're doing it, I think from a machine learning perspective is rudimentary, right? It's like a standard mixed effects model, mixed effects linear regression kind of model.
Regression.
And so
we use decision tree just for interpretability.
Yeah, it makes sense. And I think like, those types of accuracy is common with the clinically compatible type of.
But again, let's get something clarified here.
Shekhar, you would like to say something?
Yes, just one comment. I think based on what was just said is extremely important for us. I think as we define, as Professor Ganesh said, I think we should define. One of the things that we are looking for impact is to try and map the sequence in which information comes into the system. So one presumes that the 4 C's, and the 4th one I think is Koplik, something of that sort. They come in early and are very low cost, because in India I think we need to pay a lot of attention to the cost it takes to come to an early determination. So and so the clinically, I mean, we really need those 4 cases and several covariates that may be generally available. That's easy and fast to get to. So that let's look at it from an implementation perspective for a moment. If we have a cell phone where somebody can put these 4 symptoms in, along with the location and some basic demographic data that a person has, then the question we should ask ourselves is, does that constitute enough of a reason for us to tell them go further for a test? And is that powerful enough in the context of impacting both the cost and the overall, the way we attend to measles, taking a page from what was just said? We may want to focus more on that side of the spectrum and then use the ground truth as people go in for tests, etc., to refine the performance of our algorithms.
I think that's a very good point. In our case, like our relationship with the Ministry of Health in Nigeria is too low cadence. So like we talk to them not often enough. And as a result, we don't have enough ability to like change the way surveillance is actually being done. It's definitely like we're singularly focused on vaccination campaigns. And so we haven't explored, I think, enough like the extent to which this stuff is predictive of like what you would actually want to do in a diagnostic system that's cost effective and things like that. I think it would be good learning. And like
you feel there's a wealth of data we have, right?
yeah, definitely.
And given that they're giving it on a monthly basis,
Yeah.
there's this
Yeah, I think it's important.
engagement.
Yeah, I think it's really good.
Tea, coffee, tea.
Oh no, I've had plenty. Just the water is good for me. Yeah.
Thanks. Let us know if you need anything.
Yeah, appreciate it. Yeah. No, it's nice. It's yeah, we don't have, I think, this much. So like another thing that comes to mind, just looking briefly at the data that you were showing us, is like it's sometimes this is sort of a touchy subject, but some people have done the kind of work that's like based on the institution that's reporting it, how good are they at clinically classifying measles in a way that's actually predictive of test positivity. And so you can see if there's like outliers and disparities by institution and by person.
So it's assessing the institution, the mechanism.
Or the doctor themselves to see like, okay, like this person.
But it's not one doctor, right? So it's also a process-related assessment.
Yeah, and so I don't know exactly. I've seen that kind of stuff be impactful, and it's related to this, right? Which is like, is it predictive that a clinically compatible case is not going to be measles if it came from this place, right? And that can be valuable to know, to highlight like surveillance problems. We haven't done that stuff directly, but I've heard of that stuff being valuable in this kind of same space. Yeah.
I also take this opportunity, Shekhar and Rashmi and Piyush, we just submitted a paper to ICML. ICML is International Conference on Machine Learning. It's a premier venue. And this was a very extensive study we had on a deep mods versus, these non-deep decision tree, forests, and so on. I'll be happy to share the results, paper itself, the draft itself with you.
Yeah.
And what we found is, if for a particular, domain, you can get unlabeled data. Let's say we just have some census, right? Just generic children. So look at all these attributes. Can you go back to the previous sheet? Just one second.
Data sheet?
Yeah. Very interesting. In fact, Suraj may also get into it. So just imagine, let's say we didn't have all this information, but maybe 100 of these features are available for 1 million children.
Yeah.
It's pretty difficult, right?
Yeah.
Because from census, we could get that.
Yeah.
Now, we could pre-train a model which gives you the general trend, right? The correlation between the features through a deep model. And all you need to do is fine-tune that model on this 1,600 odd instances, because it has already captured generic correlations, background correlations. And the model can do very well, even with small data. So I think this is first, we studied more than over 100 data sets in our paper, and we have to share.
That's cool. That's like the transfer learning idea, right? It's like
transfer learning,
from
but
image
it's also rigorous assessment of where deep learning model standards is all for tabular. This is all tabular data.
Sure.
Okay. We can go back. Let's go to the choice of the model. Coming back, if they don't just run over the specific findings, Rashmi, take from the slide.
So basically, sir, actually he was working on it and some labeling thing, he did some mistakes. So actually this is not
correct.
This is not correct.
It's been correct.
No, he has not corrected. He will present the correct one.
Okay. So are you saying these are not the final?
Corrected? Yeah, not the final. Because
okay. But how glaring is a mistake? I know we just got the data, so
yeah, that's fine.
Yeah, but one thing is sure.
I think we can read off this.
These 10 features were coming out of 200 plus. Those were most significant. Most significant.
Means NGM positive.
What's being predicted here? Like, what is the the test accuracy, what's actually being measured? What is the decision tree being fit to?
So
It's
and that's where I feel
being-
again we need to consider.
Yeah, sure.
Shekhar?
Yeah, it's actually we have actually mangled two themes, but at this current state, essentially it fits to four outcomes. Either a person does not have any disease, or the person has measles, or the person has rubella, or the person is clinically compatible, and that's where we have mangled it. So clinically
Got it.
compatible should, yeah. So you understand that. So that's once, and the other thing is, we took the 202 features and did some basic, very basic pruning. It came down to first 178 and then now 72 features. The most important thing and the problem is the features do not contain things like when it was done. So some of the features like the IgM test is so deterministic and dominant that if the IgM test comes positive, I mean, that's just a rule. You don't even have to worry about it after that. So
yeah, I mean, the measles outcomes defined as IgM positive, right?
Right.
So
And
that feature is like
should not be included.
0.24.
Right. That's the problem. You see a dominant of the Gini index of 3 features. And so we should eliminate all 3. That's a mistake.
Yeah, I see. Because like the definition of measles positive is IgM positive.
Right.
And so like 0.24,
right.
0.24 is probably like the fraction of rows that are measles in the data set, right?
Right. So this becomes a rule-based model.
Yeah.
Can you repeat? I couldn't get you completely. So you're saying the measles IgM positive is.
See, these are we should distinguish things which are caught early where there is some uncertainty. If you get a feature which is almost deterministic to the disease, that is equivalent of actually a label. So if a test comes positive, measles IgM positive, then it means the person has measles. So there's a very strong correlation in of itself. One of the two within reason will be enough to conclude whether the person has measles or not. So we should not have those as features at all here. And that's the analysis
it's even
that
more
I'm
than
telling
that.
people to do.
Yeah, I mean, I think the definition of measles is IgM positive. So
IgM
that's not
positive.
even correlated. It's literally equivalent. And so 0.24 is like probably the fraction of rows that are measles in the data set, right?
So there's not a correlation. I mean, it's not. Oh, it's just fraction.
This is the Gini. This was a Gini. I think what they did was they did a Gini on it and tried. So it's dominant. So to the point, I think we are now moving. If I can back up a step or two, the way we are trying to this decision tree will have to be redone with the set of features ideally which are caught early in the process with a set of covariates that are done. So that's one part of the problem. One way of solving for determining whether a person has measles or not. That's like the one problem we are solving. There's about 2 or 3 other problems we've identified. One, there is an address and a location marker of sorts, like the equivalent of not a county, but much smaller than a county. Maybe it's a PIN code or a zip code in the United States, the equivalent of that in terms of either a ward or a geographical area. Then we can start analyzing and finding out information that, assuming that you only have the geographies and the counts, what can you do with that? Is there some predictive ability that we can build with that? So there is a set of thinking as to, and it's kind of, if we get the centroids of each of the geographies, and if we can get some sense as to whether collocated centroids or proximal centroids have some signal associated with disease, maybe over time, spread of disease, that kind of thinking can take place with respect to time and location in mind. Now we are in the early stages of that, but that's one different way of looking at more at a less granular level, more at a subpopulation level as to what's happening. And then there was a thinking of assuming that you have a set of 1,600, 1,700 odd individuals, can you identify the subset among this which is the most important that we need to track and identify for further testing, etc., just by some form of subset selection. So that's another area that we are looking at, and that has some support with respect to a paper that used the number of Bluetooth connections and came up with a constant to try and identify if a person has a problem, and if the level of contacts they're having is quite high, then they did an intra-group and intergroup contact, and they tried to find out, if some signals exist there to predict. So that's the third approach. So the first is just the classic ML approach, which we are looking at, but which has some errors. The second is a more location-centric. What can we do with locations and proximities, and is there some signal there? And the third is a subset selection based on getting additional data on thing of that nature. So right now, these are the three major approaches, along with the classic SAIR model that we have addressing this space. So those are the four models that the students are actually, all of us are working on. I just wanted to step back and give you a sense as to what are we working on as it relates to measles. I hope that helps.
I think it's nice. I think they should be like sort of those four approaches should maybe kind of coexist and inform one another. So like we use this kind of predictive classifier. We are not using a decision tree, using a logistic regression, but it's the same idea. And that creates the data that we put into the SCIR models. So like there's sort of a cleaning process that's happening in order to get an incidence curve that we think is representative of a particular population. And then that incidence curve is what's used to build dynamic transmission modeling. So that's an example, but in general, there's like some, I think in the four models you described, some of them will highlight, I think, better like the temporal component, and some of them will highlight like the spatial component much more explicitly, and those things are happening at once. And so it's important, I think, to like try to have them sort of learn from one another as best as possible. But yeah, I think you guys are doing a lot of work on this data, and there's a lot to learn here, so that's good.
Okay, just come to the definitions once. IgM stands for the test, antibody test.
Yeah. In fact, the first four there are basically the definition, right? So like the 1 minus blood sample collected, that's the clinically compatible, right? Because you didn't do the test, so the blood sample was not collected. No. Like that 0.18 is like, roughly speaking, has to do with the probability that a test was actually done or not. And so like clinically compatible is all the ones that the test was not done, right? Which is why it's there. And then rubella, because it's either rubella or not, right? And then measles. So like this IgM test is the lab test that's being run that determines that final outcome. It's only the one test, yeah. So it's called ELISA, is usually the technology that people use, and IgM is like antibody like cluster thing that is in your blood if you've had measles in your life recently. IgG is measles in your life. IgM is measles more recently.
And this is if measles IgM is positive, rubella would be negative. That implied no.
I think it's pretty rare to get both at once. In fact, so it's assumed that you don't have both at once because prevalence in general, even in high outbreak settings, is low per person. And so it's like flipping a very low probability coin and getting heads twice, I think. In principle, it's possible, I think, but I think you don't see it very often.
And what's this equivocal? Equivocal would be in,
it's like unclear if it's positive or negative. So these tests are done by like optical dilution. So they take a serum sample and they keep diluting it and then putting in a compound to see if it reacts. And if it reacts, it means the antibodies are there. And the reaction is like actually the plate that they're growing the serum sample on turns blue. And that blue changes into lighter and lighter blues. And so they do like an optical transmission measurement on those plates, and that's how they measure positive or negative. And there's a threshold. a dilution threshold that counts as positive, dilution threshold that counts. And so if you're too close to that threshold, that's equivocal. That's what that is.
And ACS would be what?
So actual case search is used.
Yeah, I've never seen that before.
ACS. So this is a fraction of the 0.18. The one that
I don't know.
was collected.
Yeah, I don't know about that. That's, yeah, I've never seen ACS. But I know like in some areas, I mean, they do contact tracing to try to see if like other people have come into contact with this person who had measles. And perhaps it has to do with that. But if it might be follow-up ACS, but I don't know. Yeah.
Do we have to finish it some? So the remaining 82%, we would not have any results for measles rubella. So it's basically 82% are the clinically compatible. Yeah, the 82% would be clinically compatible, right?
I don't know. That number's a Gini number, right? So it's maybe not quite so.
But roughly of that order.
Yeah, it's like seems that way. Like they're basically split into quarters, but
Active case search, not actual.
oh, okay. So sometimes rather than having passive surveillance, which is like people come to the hospital with symptoms and they decide to test them, the doctor does. If it's known that an outbreak is happening somewhere, they'll send people to go find measles cases. And that's what they mean, I think, by active surveillance. And so from a sort of like statistical sampling frame kind of back mindset, it's quite different than passive surveillance, right? Passive is like measles made you come to me. Active is like we came to you because we thought you had measles. And so you might want to separate that data from the other, like the ACS data is perhaps measured quite differently than the passive surveillance data. But we've actually very rarely worked with ACS. Most surveillance in the world is passive for measles.
I see.
Yeah.
As in an experiment.
So should we have 0.04% or 4% of active? This is interesting.
Yeah, 0.004.
Oh, it's 0.004.
Yeah.
4%.
Yeah.
Yeah.
Pretty small. Yeah, I think that's common. It's pretty hard to do active surveillance. So you kind of rely on symptoms to drive people to the clinics, and that's the surveillance mechanism.
So sample collection is going to be subset of the blood sample, right?
It's a different test.
They have this data set they have separately protected this. Other than blood.
Yeah, so throat swabs there's a few different, there's like actual blood draw, there's dried blood spot, and then throat swab and nasal swabs. And all of them are different tests. I don't know much about the throat swab.
Can we just go to the spreadsheet and we can just quickly look at filter, right? We can just filter by, we should really do the filtering.
Which one?
Filter by the throat swab, right? And we need to check if all throat swabs have blood samples as well.
Oh, they do. Interesting. What we did.
So this blank is not taken, right? Going to be the.
I don't know. There's a one on the call before that. Doesn't that mean
No,
they?
what is it? What's the sheet? Can you go to the zip?
Oh, there's two throat swab sample collects.
This
EY.
What's the definition?
Oh, condition. I see. So collected is ET and condition is EY.
And collected is?
ET. That's what you were looking at before, yeah.
Okay.
And
Collected and it's a condition.
What's the difference?
there's some measure of like the sample integrity condition, I think is usually that's meant by, but I can't say how common it is to get a sample that's
So
not.
result is another column.
seems like we need to really hurry up on our understanding of the data instead of just.
I think
That's
just
not
the
the
test, yeah, like getting a sense of like how the testing system works will go a long way. And you can, I can maybe send you like there's like nice reviews of like how measles surveillance systems generally work, and the ELISA test, how does that work, and this twofold dilution. I can try to find some good literature for you on that. I think will be something you can read in an afternoon, and it'll clarify everything that you need.
That'd be great.
Yeah.
Especially Megan.
Yeah. I have a colleague who's has a more biology background and will be able to point us in the right direction on like what a good thing to read is. But do you know this Hopkins vaccine book? Big. It's the biggest book I've ever seen in my life. It's the like a big biology book on like all the different vaccines, history and technology. But there's a measles chapter, and the book is free. It's online. And that measles chapter has like a very good level for people like us who are not like clinicians, but has a general sense of like history, but also like how was the vaccine developed, and also how does surveillance work, and like what's the pathology of measles, and like just a very kind of like high level introduction. And that's a nice thing to read as well.
I see, but this data goes beyond vaccine.
Yeah.
I'm non-vaccinated cases.
Oh yeah. But the vaccine book kind of has like a motivation for the biology of measles and why the vaccine works the way it does.
So did you remember the name?
Plotkins, yeah, like PLK. Yeah, there it is. Plotkins vaccine. It's a Peter Streeple, a few other people wrote the. I think it's online for free. That isn't free.
Maybe I'll
Okay, I'll figure out how we have.
go back. I think it's on.
It has a chapter. Yeah, don't buy it. We'll figure out how to get you access through what we have.
Ebook.
But it has a.
PDF has the book.
Sorry?
PDF drive link has this printout.
PDF drive. This is a PDF drive.
Now, this one.
Yeah, you can search for that. Oh, this one.
This history of the pillows.
I don't know the same exactly. I think that's a different book. It's the same guy, different book.
Title is different.
Yeah.
Go download it.
But anyway, I can find out how we have access. We have some online version.
Yeah, I think we've just been linking to.
It's a huge,
Standing.
yeah, it's like this massive book. So,
Oh, it's me. Okay. We'll take care. Bye.
yeah, you should email me and I can point you to some of this stuff.
See,
Results. So this is
filter by filter by throat swabs.
okay.
On ET, right? I thought you were
E or E.
ET is like if it was collected.
That was coming significant.
I meant collection. This is
Okay.
collected. So did they collect samples, throat swab samples every time they collected blood samples?
Right.
Are the two
Yeah, it's a good question.
one cell in the
So is there a blood sample column too?
Yeah. Before blood collection.
last day?
Or maybe EJ? I think EJ looked kind of.
J. Like, yeah, HA. So you're already filtered by sample collected, right?
Yeah.
And is that sample collected always one?
No. I put filter over there, na? So that is why.
Yeah, you haven't filtered.
put filter at
AP and EG, right?
yeah here.
Oh, you have filtered. Excellent. So you have filtered. No, no, I'm asking.
Yeah.
Okay,
Yeah, that was
fine.
good. Yeah.
EG.
Looks like they might collect
Both some
um
So there's no zero here, right?
that one,
zero.
that like reason column.
Okay. Oh, there are zeros.
Reason.
Oh, there are zeros. No blood.
There are zeros.
There are zeros.
Yes. Yeah.
Okay. So one.
Interesting.
That's a subset of.
I think blood samples like gold standard. Um,
So you don't think it will be a subset of. I mean, throat swab should be much simpler than blood. So maybe throat swab is.
I think, but it's not considered as accurate. So they usually try for blood first. I don't know the reason.
Throat swab is done blood.
I don't know actually. Maybe it's faster.
Can we just quickly check if, let's say, filter first on blood sample, right?
Sure.
If all of the throat swabs are one, it certainly means that throat swab is a superset. Blood sample.
So again, we are getting some zeros here.
Yeah, I don't know how they make.
Throat swab will be zero. Can you filter on blood?
Oh,
Yes.
yeah, it's done.
I have a filter on blood.
Yeah, yeah.
Okay. Oh, that has zeros.
Yeah,
It has zeros.
Overlapping.
yeah,
Interesting.
yeah. I don't know how they make that decision. Where did you say the data came from?
The Mumbai Municipal Corporation.
Hmm,
BMC.
I see. So these are like private hospitals, or?
Government.
Oh, okay. Okay. I see. And so, yeah, I wonder if you could talk to them too about how
Can you make a visit to them tomorrow or something?
that decision is made.
We can find out and since they haven't responded to emails, we should just go and meet them. The sooner we can get clarity, the better, I think.
Yeah, it's good. Yeah. But I don't know. I can't say I've worked with any throat swab data. You hear about it sometimes, but for us, it's always IgM testing. That's, I think, what's considered like gold standard. What measles definition is IgM positive. Yeah, I haven't seen. Like more recently, Foundation is starting to make some investments in like lateral flow assay kind of measures. So that's like the COVID at-home tests. That same technology you can adapt to measles, and so they're making like rapid diagnostic tests like that. And we'll see where that goes. And so that's like a nasal swab or a throat swab that you do at home, right? So I wonder if there's some reason like why they're testing particular throat swab technology or something like that here, but I don't know. Does it change over time? Like if you do this in 2019, is it very different?
2019, do you check that? That's interesting question.
Blood sampling changed. Column changed. Is E. Yeah.
Is there even the throat column?
The throat swabs.
Oh yeah, there it is. Okay, so they've been doing it for a while. It looks like there's more zeros,
More zeros.
but oh, can you actually?
Same stuff. We are getting
Fine. Fine. So I honestly feel we are targeting a wrong problem as well. I think from the initial part, if you can go back to the decision tree or whatever, right? I mean, we should not be predicting four-way classification. It makes no sense. Why should we try and predict it's clinically compatible? I mean, for the clinically compatible cases, building a model that can predict whether it'll be positive or negative.
Yeah,
That will be of value.
that's I think why we did it that way. So using the IgM data as gold standard, and building a covariate-driven model that tells you if you performed an IgM test on this person, what's the probability you think it would be positive or negative? So that's only using measles IgM and measles discarded ones, or we group rubella into discarded, right? Because it's like not measles. And so in general, we're trying to think of like, what's the probability that someone has measles at a given time, given that they have the symptoms. And that's, I think, the type of question that is thankfully a little bit simpler than this one. And also in the sense that it's binomial, right? It's not multinomial. But yeah, that's
So trying to predict for the clinically compatible cases, who should be subject to.
Because if you wanted to plot something like cases over time, right? It's unclear what to do with the clinically compatible cases. And for a time series model of disease transmission or something, spatial model of disease transmission, something like cases over time is a very important input, right? And so we do some work to make that input as reliable as we think it needs. And lots of times, like what'll happen is like there's like in less stable surveillance systems, there's like lab kit stockouts. Like ELISA, the technology requires some chemical reagents, and sometimes they run out at the labs. And so there will be extended periods where like measles is not positive ever and everything is clinically compatible, right? And so like you have to be able to interpolate across those time periods. And so like we want models that are robust to disruption, and these kinds of back-end technologies is how we do that. Yeah. But because like we wanted to, I think the reason we didn't use something like a decision tree is because we wanted to have a prior that it's something that's very smoothly over time, because the data is sparse in time, right? And so some kind of Bayesian regression methods, they fit nicely with what we wanted to be able to do as far as like temporal smoothing. And so we have like if maybe this is familiar terminology or not, there's like a random walk, second order random walk in time. And that's like what's the prior that's being put into this like Bayesian regression logistic regression model. And yeah, that's how we're, if I had my computer, I would show you, but it's up to the math department.
Are your slides anywhere on email or something?
Like I have.
You have.
Yesterday,
Those slides don't have this. This is sort of separate. I'm trying to think if there's a way to show you.
So as he pulls that up, even the subset selection problem, this is actually right. I don't think we should look at anything beyond this data. If identifying, maybe geospatially identifying a subset that needs to be tested.
Right. Yeah.
For let's say we want to validate our hypothesis, even a decision tree, what's the subset that we should test? I think this is great.
Yeah, I think that's
a gold mine of data which we didn't realize.
Yeah, I think you're right. And I think there's like, and it also just a lot, like, I think you mentioned this, Shaker, like there's a lot to be learned about mapping the sort of pipeline from like a child gets sick to a case gets reported. And there's a lot of times where things can drop out of the system before it becomes a case, right? And case detection rates for measles are generally quite low. So the highest, like in extremely functional health.
What is case detection here mean? Sorry,
like the probability that you're infected, but you get reported a row in this, right? Like that probability in like Lagos State, Nigeria is less than 1%. Right? I
still didn't understand the probability of a false positive.
The probability that like you have measles, just because you have measles doesn't mean it gets reported. In like in highly functional care systems, that number gets left to 50%. So like it makes sense. Like a lot of kids who have measles, they just stay home. They don't go to the clinic. And so like you can ever get every measles case, right? Because a lot of people bother or don't need to go to the hospital, right? And so the fraction you get, like subset that for whatever reason is to the clinic, could be something else with them sick, or maybe they have a relationship with the hospital and they end up going to whatever. That's like a driving force in what actually you detect. And so getting a sense like where the bottlenecks are prevent people from becoming cases. So that's like the terminology of just like Measles infection means that your body. Measles case means report to a surveillance system. And those are often very different, right? One's a subset of the other, but it's a smaller subset.
It's moving one step behind even the legally compatible cases. Because
Yeah.
legally compatible wasn't tested, but it didn't even up to a clinician.
Yeah. And so like, that's been the issue, right? And yeah, in most kind of like LMIC, low middle income country settings like we're working with the foundation on, it's very low numbers. And so you have to be able to make inferences that are robust to like a very small subset of reporting. And classifying like the quality of the surveillance system, that's something that like is becoming a bigger and bigger, I think, like programmatic goal.
Yeah.
Connect करना? You like to send your file to me or ये connect करना है?
I'll just be back.
Okay, please don't connect. I'll send you the.
ठीक है.
I'll just be back from a very short meeting. Please continue.
Yeah, sure.
Just 10 minutes.
Yeah, that's fine. That's fine. I'm looking for those slides. See if I can.
I had a question. In terms of the work that you did, in terms of classifying and the logistic regression informing the SCIR model, can you tell us a little more on that? Because I think that's interesting to understand. What did you do with that?
Yeah. I'm looking for a set of slides that I have that
Okay,
I
sure.
sent to people like early last year. And if I can find, I think it will clarify a lot. Just give me 1 second.
Yes, sure. And we also used, just to reaffirm, we used also smoothing for COVID. And we also used the Bayesian approach, and we used averages within the last few days, etc., to kind of smoothen the curve before we did the predictions.
Similar idea.
HDMI
15.
meeting link being but it is not visible to Shikhar sir.
Yes.
Meeting link just
Else from this year on my phone.
vaccine connects.
So like kind of unlike your guys' situation, it's quite large. So that's because this goes back for over a decade. So this data goes, you can see 2007. That's it's chronologically ordered, so like it was pretty big in that regard. But then demographically speaking, we have to rely on survey data. So there's no birth registry, there's no immunization registry, there's no death registry or anything like that. So like getting a sense of those types of quantities, it requires us to work a little bit with essentially DHS survey, also mix survey, and they run some surveys internally. And then there's a separate group that's funded by the foundation called Geopode. It's also group 3. See that kind of work. It's very machine learning, satellite imagery heavy, to try to do like a structured population estimate. So that's the way we get like, because Nigeria, for example, doesn't have a census since 2006. And so in some sense, like we're doing a little bit more of piecemealing than you guys are going to have to, which because of the kind of data situation, but also the data set is larger than what you guys have. And so like the types of things that we have to do, and this is like really what I had in mind when I was talking about this logistic regression. So this is one state, Lagos state in Nigeria. And so like that top panel there is time series. The dark gray is lab confirmed and epidemiologically linked cases. And so you can see if you're like following it along. In 2013, the dark gray just disappears, right? Oh. I tried that. I don't know why that happened. I got a text or something. Oh, I'm having network problems. I'm not on the Wi-Fi. This is not using my phone service.
If you could send me, I could.
That data is not ours to share in a more official capacity. So I know it's easier, but I shouldn't. Or unless I could send it to you, have to delete it. Or something. We can do it like that.
Yeah. So this was state-wise data. Nigeria. So you just
What's being plotted is state. We have it down to district level. In that regard, it's somewhat similar. Maybe one more sound. And then if it doesn't work, I'll you can email it. Or something like that. Oh, that's the wrong thing. Too many slide decks. This is a good one. To connect, yeah, I have to check that. Sorry about this. Okay, let's do it this way. That's fine. Is it okay if I send it to you? And yeah, like maybe we can delete it after. It's just it's kind of there's a sort of data sharing question here. Sorry about that. But worked well briefly. Almost good. Okay. And emailed it. He rushed me response to that. Take a breath.
I didn't receive it yet. Yeah, yet to receive.
I thought it's just like. Yeah. Sent on my end.
Refresh ही कर रही हूँ. Yeah, कई बार अभी आया. Yeah, now got it. Forward कर रही हूँ तो.
WhatsApp.
Email. पीयूष. पीयूष आगे क्या है? Dot S. He worked on contact tracing portion.
Oh, that's great. Yeah.
Would like to.
That's great. Yeah. Yeah, I think we can be brief about this. I can just show you a little bit like what we have in mind. Specifically for like the data preparation stuff. Which I didn't really talk about yesterday. Talked a little bit about the models themselves. Yeah, so if you go down to that same figure we were at. Yeah, so where we left off, so the dark gray is like the IgM positive, and then what I was saying before, epidemiologically linked cases, right? So those are ones where someone in the immediate vicinity, like brother, sister, or something like that, friend, was IgM positive. And then this person has symptoms, they don't bother to test that, they just call it epidemiological linkage. So the dark gray you can see is like dominating initially and then vanishes. So that vanishing is a lab kit stock out. That happened in 2013. So all of the cases become.
I should do screen share, I think.
अच्छा हाँ. Others are not able to. Yeah. Please. It's to yours. Yeah, this one. Shekhar sir, I hope slide is visible to you.
Yes, now it is.
So I'll just repeat then a little bit. So the dark gray going in the top panel, that's measles cases in Lagos state for time. And those are specifically the ones that are IgM positive or epidemiologically linked to an IgM positive. So that's like gold standard measles cases. And you can see there's a tiny amount of clinically compatibles like in 2012 and stuff like that. And those are ones that are untested, same as your guys' data. And then in 2013, there's this like stock out that happens. And there's quite a few clinically compatible cases. And then, it sort of moves back and forth. There's some testing availability, some not, depending on the year over time. In the backdrop for Lagos State, routine immunization coverage is increasing over this time period. So like they're achieving better and better measles control, specifically because of like campaigns and stuff that happened in end of 2015. And so you can see like cases start to become less and less common over time.
But during 14 to 20, there is a huge gap between the red portion and the gray one.
Yeah. So on that, so the red portion is what we put together with one of these classification models. So what's not being shown here is throughout this entire time period, there are rejected cases as well. So that's like lab discarded. So they clinically compatible. They come to the lab, they get tested, and the test is negative, right? For measles. And we use that data to build the classifier in the second panel. So the second panel is like the bars are the mean estimate and binomial error bar associated with the number of discarded cases and the number of positive cases. So like that's essentially the data that we're using in a logistic regression. And then it's being done at the row level, like individual level in the line list. So where the drivers of this estimate are like the age of the person, whether or not they had a dose in the past, whether or not they, what time in the time series it is, etc. And we generate this like yellow estimate. That's the probability that if you're clinically compatible at this time, it's actually measles.
Mhm.
And in Lagos State, you can see it's quite low for the most part.
Mhm.
That's not true everywhere in Nigeria, but in Lagos State, they have been achieving control. And so like this thing has like dynamic character. You can even see the impact of campaigns. So like those big dips, that's like when campaigns were happening. And that's what we use to make the red curve. So the red curve is the thing we actually use for input into transmission models. We don't use the dark gray and we don't use the light gray.
Okay.
And so you can see it kind of gracefully deals with this lab kit stock out, but then later on, there is clinically compatible cases that it ignores.
Hmm.
And that being ignored is compatible with the data that we're getting at the time. So that might have been rubella, it might have been something else, but it wasn't measles.
Yeah.
And so we try to make the red curve to the best of our ability an accurate representation of incident, which in practice, I think is neither the light gray or the dark gray. It's something, right? So like, as you guys are working with that data, I would encourage you to try to make some like visualization like this that tells you if like, what fraction of clinically compatible cases are you actually capturing? Which do you think are actually measles and not? And then like, as like Ganesh and Shaker have been saying, like there's something to be learned about the healthcare system from just like this yellow curve. Like what drives the structure of this yellow curve. Essentially, you guys can do this with a decision tree or whatever. It doesn't have to look like this, but like I think you understand what I mean. And that process will hopefully shed some light on like where should tests be directed? How can you influence the healthcare system to be more effective at delivering tests to the right people? That sort of thing. And that's the type of lever of power we do not have in Nigeria yet. Like we don't have that kind of influence over the way the surveillance system happens. What we do work with is vaccination campaigns. And that's like kind of the level of the relationship at the moment. So for now, this just lives on the back end of our transmission models. We haven't published this. It doesn't live anywhere. It's just sort of like one of the data cleaning tasks that we have to do. But we try our best to validate these models. If you go to the next slide, that shows that it fits the data. This shows that it is kind of a epidemiologically relevant kind of quantity. So now in that scatter plot, each of the dots is a state in the country. And the y-axis is the time average version of that yellow curve. And the x-axis is the average coverage in measles vaccination coverage and survey. And so you can see, like, if you live in a low coverage state, something that's clinically compatible is much more likely to be measles. And if you live in a high coverage state, something that's clinically compatible is much less likely to be measles. That's good, right? That's one thing, that feature that the model is capturing kind of on its own, which is good news. And then we do some stuff like to see how the age works and to see how self-reporting works. And so like the colors there are the model features, like basically like the logistic regression probability changes as a function of being in these age bins or being in these self-reported doses. And then the black line is like what's actually in the data set.
I'm sorry for saying it's part of.
Yeah, I thought you would actually. Yeah, my bad.
I'm really sorry.
Can
I ask questions?
yeah. You might benefit from seeing the slide before. Actually.
Sorry?
Can we go up one slide again?
If you don't mind.
Yeah, no, not at all. So like this is kind of what we're doing that's related to the same thing. And so this is data from Nigeria, and maybe go one more slide up actually. So to give you a sense of like what the data looks like, a screen cap is there in black and white, that like sort of control panel looking thing. So those are the columns that we actually, and we have more than this, but this is what we actually use to time some space stuff that we have. Classification is essentially the same thing as your guys' outcome. So 0 is lab discarded, NaN is clinically compatible, it's empty, and there's ones there that are lab confirmed. And then we have some ages.
You're not classifying into clinically compatible, obviously. Right? We did the mistake we did. You're avoiding it.
That's the point of this exercise. So just hold that question for a second.
Oh.
So some of them are lab, all of the 0s and 1s are lab confirmed or lab rejected, respectively. Or sorry, reverse respectively. And then the age stuff is stuff we have from the clinics when this kid was born. And then they asked the care provider of the child in a lot of cases, like, hey, have you had a measles vaccine before? So the number of doses is that final column. 1 dose, 0 doses, right? They don't know that kind of thing. And then one key difference, I think, between our data set and your data set, yours has a lot more information than one, but ours is bigger. So like you can see the number of rows. It's because it's going over like 10 years.
2 lakhs.
Yeah, more than that, 2007 to 2020. Okay, so then if you go to the next slide,
This is, yeah, I see, individual.
similar to yours, yeah.
Mhm.
And so this is for one state.
Mhm.
In the top panel in dark gray is all the lab confirmed and what I was describing earlier, epidemiologically linked cases. So those are the ones that are like gold standard measles cases. Light gray is the clinically compatible cases of this particular study. And so you can see, like, if you took the light gray plus the dark gray, it's a very different picture than if you took just the dark gray. And so what we do is we fit a regression model. What's not being shown here is the rejected cases. But in the second panel, you can see the fraction of cases. The black lines there are like point probability estimates with binomial error bars for the fraction of cases that are rejected versus the fraction of cases that are confirmed. And the yellow estimate is like time, is the time component of the logistic regression. And so basically it's like saying this is the probability that if you're clinically compatible at this time in LEGO state across all the demographic variables like age and dose history, this is the probability of being actually measles. And so like there's some features you can see. So if you look at 2013, the dark gray like disappears and becomes light gray. That's an example of a lab kit stocked out. So there's like a documented situation where the lab ran out of reagents at that time. And the red curve is what we actually give to transmission models, which is like leveraging this regression model to dynamically sort the light gray into what we can. And so that's the type of thing that like we have for every state, and we think of this as like sort of a data cleaning piece of this work in the process of building the types of transmission models that we want to build. But we also try to check that these models are accurate. So where you came in the room, next step is this slide where we're just trying to say like across all states, does this capture the types of things that we think are correct? For example, that reporting more doses is associated with being less likely to be measles. That's what's shown in the purple. Or at young ages, you're maternally protected. At middle ages, you have a high likelihood of being more measles positive. And at older ages, you're more likely to not be measles because you've had measles already, right? So that structure is what we expected to see as well. And then this correlation with vaccination coverage is also the type of thing you would expect to see, that if you have a higher coverage population, a fever and a rash is less likely to be measles than if you have a lower coverage population. And so like, this is broad scale kind of features of these regression models that are being fit state by state by state. But we are using them just for this purpose, to make the red group, to do this interpolation of clinically compatible cases. And so that's what I had in mind.
So, but you couldn't go back in your case, right? Because there was a time lag between
Yeah.
you.
And also there's like a relationship problem. Like we just don't have we're not in Nigeria all the time, right? And I think it like matters that it's hard to kind of do the influential part of it. So like we have a good relationship with US CDC and with a lot of other folks in Nigeria too, like it's NPHCEA is what they call it. It's the public health organization, right? But it's very immunization focused. So like these types of like, how do you make the surveillance system more effective? Those questions, they don't have time to work with at the moment. I think they're so focused on just that's.
Could you work with us on our data?
Yeah, if you want to. I think
That'd be great.
to be like just one piece of clarity. Like I want to make sure that you guys have ownership over this stuff, specifically for the health of NDMC and like my work with Arinda. So like a part of my life is that I'm not just a researcher, I'm also part of the funding side of the foundation. And so I would want to take a backseat role. I'm happy to do a lot of like as much work as you guys would let me. But like it's I think important that I'm not feeding anything for sort of consortium health reasons and things like that. Like we want this thing to kind of stand up on your guys' work. And so I'm happy to share code and do all this kind of stuff and even work with the data, but it shouldn't come from IBM. I think it should come from you. So as far as like authorship and stuff like that, I might decline, but like I'm happy to be part of it.
Okay.
So there's a few other data processing.
This is very interesting.
This is how the measles models, but this is the inside. And like
the interesting thing is we can do what you did, but going beyond that,
Yeah,
we have a live line.
yeah, I think that's great. Yeah, yeah, and that's the whole goal, I think, of what we're trying to do. As well as like, this is, I think, like from a biostats perspective, kind of basic. I think you guys have a lot of machine learning experience that I do not have, and so it's possible to do this a lot better. And I would love to see like the kind of innovation that you guys come up with in this space. But this is, I think, like a representation of state of the art in global health. And
Did you publish this?
no. So and this is an important point. Like I'm actually not even allowed to share these slides. So like we need to delete these copies of these slides because I need to clear it with the people in Nigeria to do that kind of thing. So
But were you able to give back the report to them?
so yeah, they have access to it. Like we go back and forth in that kind of way.
So you did.
Yeah, yeah, and that's this stuff gets presented routinely at like calls and stuff that we have with them. But publication is complicated.
I see.
And so as a result, like a lot of the measles work that you'll see published from me is old. And that tends to be how this works. So maybe this stuff gets published in 2 years from now, but not in a way, it's purposefully like not in a way that's.
So as far as publication is concerned, even we are clear, and we can simulate data. We have, in fact, we are to present some simulation models.
Yeah, good.
I think our main goal right now is to be
Impactful. Yeah,
impact.
yeah.
And the fact that they're listening to us.
That's great. I think that's
So
a good
let's
way to do it.
make that impact.
Yeah, I'm with
Everything else is secondary.
So there's a couple other things that I should put on your radar that you guys should think about. So if you go to the next slide. The other thing that's like kind of a component that matters, but you guys have birth registry, right?
Yeah.
So you should just look and see what this looks like. For us, we don't have birth registry. So one of the things that we have to estimate from survey is the seasonality of births. So like people are more likely to be born in certain months than other months. And that seasonality can be quite pronounced. So this is an example from one state, Jigawa State, Nigeria. And the y-axes are shared. So you can see like February is high and November is low. This is the probability of a birth happening in those months. And so we fit this with some like essentially multinomial smoothing model. That's the gray. And we use those probabilities as input into the models as well. So we tried to make demographic estimates that are basically a replacement for birth registry. But one thing you'll find in these dynamic transmission models is that the seasonality between measles and the seasonality between births are things that can resonate and interact with one another. And so like if you ignore something like birth seasonality, you can get the measles seasonality wrong, you know, like a kind of a regression framework.
Did this help you the modeling as well, SCIR modeling?
Wait, sorry, say that again?
In your disease modeling, the SCIR modeling was birth cyclicity or what, birth periodicity and input at all?
Yeah, that's right. In the stuff I was showing yesterday, which is in this slide deck, the like outputs, it uses this kind of input. So that's one thing. The next thing to probably think about too, I think this is not so relevant for you guys because you have birth registry, but the next slide I think maybe is, which is like changes in the age distribution of measles over time. So this is now done by region for us because of like data restriction issues. But like as measles control changes over time, so does the age at which you get measles. Like if there's less susceptible people in the population, kind of from a simple survival analysis argument, like you make it to older ages before measles gets to you if you're unvaccinated. And so that's what's happening here. So like in 2009, measles control is not as good as it is in 2020. And in 2009, the peak is lower than it is in 2020. And so that shifting of the peak, that changes how you might think about like when you should expect to see cases, given that a certain person is born in a certain year. And we use that to build priors for the transmission models. So basically like the way we deal with this underreporting issue that not a lot of cases are reported is that we use this age distribution as like a kernel for when we expect the birth cohort to appear as a measles case, right? Okay. And so that tells us like when and how many measles cases we should be seeing. And that gives us a baseline with which we can set up a prior distribution for reporting rates, like the fraction of fractions that become cases. And so like holistically, the way that the data ends up looking after we do all this processing is on the next slide. And one of the things that we do that we found is useful is these like data profiles. So yeah, if you go to the next one, this is for Lagos. This is essentially like a representation of a lot of the data we have. So you can see the birth seasonality that comes from that method we were talking about. This incidence data is that same red curve from before, but daily. before it was being plotted monthly. And then we have some vaccination stuff. So we do like kind of conventional biostatistics to do the smoothing between surveys. That's what's shown in purple. You guys don't have to do that. You have registry. That's good. And then we have campaigns, and you can, it's in yellow, so it's a little bit hard to see, but those are when vaccination campaigns happen in Nigeria, in Lagos state, and you can see the size of them is quite big, like 1.2 million doses, 1.6 million doses given out in those times. And so the whole goal is then to take, like, building this input is really the word. And then we use the methods that are similar from that PNAS paper about Pakistan to then turn these into SIR models. And so that's what the rest of the slides is. And that's the kind of stuff I talked about yesterday. But like, I didn't really talk about the data kind of process because I figured we would have a conversation like this.
This is very interesting.
So we can talk about this in a lot more detail. Perhaps I'm supposed to meet people at 5.
We got 10.
The students. So
Okay.
maybe
a couple of minutes.
yeah. And so yeah, because I want to hear about what you've been up to as well. Trying to remember what else is in this. Can you just keep scrolling? There might be something else wrong.
Run through the slides once.
So there's two
I missed your. Sorry, I missed your
talk yesterday. That's true.
Just complete the story.
Okay.
Really glued into it.
Okay. So I showed 2 examples of this, right? These 2 different states. One of them is Lagos, one of them is Jigawa. You can see how different birth seasonality is, the vaccination profile and stuff like this. That's the whole point of these slides. Next slide. So then that's like the data processing process. Now we get into transmission modeling. And so this is like a schematic representation of the transmission model, which I think you guys have seen roughly before, which is basically like you're born, you have the opportunity to become routine immunized. If you're not routine immunized, you become susceptible. Susceptibles have a few options of what can happen to them. They can either be immunized in SIAs or they can become infectious. The process for becoming infectious is correlated across spatial regions. And it's a little complicated how we do that, and I think we can probably do it better. But in general, like basically our seasonality estimate is pooled spatial regions because like the data is so sparse. And so like what counts as a measles high season and a measles low season comes from information from neighboring states. But then like the model lives itself at state level. And then infections have some probability that changes over time of being observed in terms of cases. So that like C sub T is the actual incidence curve. That was the red curve. So if you keep going, this is an example of the model output. This is the slide that I showed yesterday. So the black dots there are the same red curve that we got from that regression model, the logistic regression model for Lagos state. And then that gray region is the transmission model fit to that data. And then what we get for doing all this work is estimates of the things we care about. And the 2 things we really care about are susceptibility in blue and reporting rate in green. And so susceptibility is like the fraction of the population that is missed by vaccination and is currently susceptible to measles. And one of the things that we try to get a sense of is like how effective are campaigns. So I showed you like 1.6 million doses being given out. That number now is the number of people that are immunized in that campaign. You can see it's like roughly like 1 in 10. Lagos state. So like 1 of every 10 doses they're giving out in the campaign is actually immunizing a child. The other 9 doses go to kids that have already had measles or already had vaccines or already, for whatever reason, are not getting immunity. Vaccine fails, etc. And then the reporting rate estimate, that's what I was describing in terms of the age distribution. So that gray region at the bottom, that's a prior constructed from these survival analysis arguments. So we take the age distribution, we map birth cohorts to when we expect to see them as measles cases, and then we compare that to what's actually being reported. That sets up the gray prior. And then in the process of model calibration and fitting, this algorithm is actually published, so I can show you a paper on how to do this. It's applied to data from the UK, not to this thing. That method generates the green, which is like day-to-day estimates, or in this case, bi-weekly estimates of the fraction of measles cases that were reported.
We have all of this. We can get access to.
Yeah. So you guys could reproduce this, I think, and I can give you code and stuff. That stuff is easy.
Very exciting.
It's a question of like, I think, where do you guys want to take it after that? And I think there's a lot of good options. But of course,
I
like,
just want to avoid the false starts that we have.
yeah,
We
that
spent
makes
a
sense.
month with some false starts.
Yeah, that makes sense.
We don't want, and not for us, right? Not for publication's sake, but for the people's sake. I mean, they're sharing data with trust.
Yeah, hey, you wanna
If you don't give
reduce
them
it.
back, some analysis in time, it's a disservice. Right?
Yeah,
And
yeah.
then they will probably lose interest in sharing data,
That's true.
and rightfully so. I
Yeah.
don't blame them for.
Yeah.
I've been on
So
top of this. We
the
need to communicate to
the
them.
goal for us is often forecasting in measles. So the next slide is an example of how we test these models for forecasting. In Lego state, it's perhaps not so interesting.
Mhm.
Cases are very low, and in this case, we would have underestimated the performance of the 2019 campaign.
And this is what they'll understand. See,
Yeah.
this the regression models for them is good,
Yeah.
a little Greek and Latin. This they'll immediately.
Yeah, so like, why would we have gotten this wrong? The way we get this wrong is like, we look back at past campaigns. We say like, okay, about 1 in 10 doses are immunizing. But 2019 actually outperformed past campaigns. And there was a change in 2019, they age restricted. So instead of doing it from 1 to 5-year-olds, they did it from 9-month to 2-year-olds. And so it was much more targeted. And the 2019 campaign per dose was like the most effective campaign in Nigerian history. And so we would have been overestimating our forecast. You can see that overestimate in the top panel. If we correct that, which I think is on the next slide, I don't remember. No, actually, this is the model for Jigawa, and Jigawa's model is perhaps equivalently predictive. In that case, we don't have this SIA related issue in 2019. And so you can see like the outbreak structure and stuff like that is quite predictable. It's because seasonality is quite predictable. And then the uncertainty really is demographically dominated. So some of those outbreaks could have been worse or better. It kind of depends on reporting or understanding a little bit better what is going on the ground. But these types of forecasts are what we use to start planning immunization campaigns. And so like getting better and better at this forecasting problem, that's what we're working on in this space. And then I don't know what's next. Probably nothing. Yeah, it's just the conclusion. So this was like a document that was meant to be read by people at the PHCA. And this is the type of way that we tend to communicate with them. And so I have like thousands of these types of slides because that's the kind of way that we inform these conversations. And, it leads, I think, to some good things. Like we write applications to Gavi with them. So there's like sections in the Gavi applications that look like this and are written by us to justify the case for campaigns in certain places. And in that way, they're able to secure money. And so like, that's, I think, like the functional part of what we're doing with them. But there's a lot of like science that we don't get to do, which is like questions about like, okay, how do you structure a surveillance system to actually be more effective than this? We are always in a rush with that, right? To do the immunization campaign spend. So we never get to go back and like ask this question of like, okay, like what does this actually teach you? And so I'm hopeful that you guys get the chance to do that kind of stuff here, because like what I would love as an outcome of this is like you guys publish papers that teach that we can cite as like, hey, in Nigeria, we should be doing things this way. That's, I think, one of the key goals of the ndmc. And something that the DIMC is not very well positioned to do. And so, yeah, as far as like my role, I'm happy to support as much as you guys need me to. In different roles, like if you guys want to interact with the IMC people, I can facilitate that. And then simultaneously, if you guys want to be able to do this kind of stuff quickly, of course, that's even easier than the IMC stuff. So that's roughly speaking, like where the measles work is currently at for us. And there's perhaps a paper you should read on that survival analysis reporting stuff. And that's on archive, and it's like solo authored by me last year. So it should be pretty easy to find, but I can also be helpful. And that's like a nice place to see a little bit more about like algorithmically, how do we go from data to transmission model? Yeah. Yeah, of course.
I'm going to summarize the to-dos.
Yeah,
in
yeah.
Rush. I think the first and foremost to do is, since our feet are on the ground, the MCGM, we have the data and the instant corporation. We would reach out. I mean, if you the sooner you can share your code,
Yeah.
just to get a baseline and think of it as a baseline.
Yeah.
Both in terms of the data-driven prediction model and also the transmission models, right? That will be really nice. We can share code for both.
Yeah.
Um,
A place to begin. There's a GitHub repo
okay,
associated.
it's already there. It's public.
Not for all of this, but for the stuff associated with the um, UK data, which the UK data is actually much more similar to your guys' data in the sense that they have birth registry, but it's pre-vaccine era, so there's no vaccination. And as a result, it's not always the most relevant thing, but we publish with it because it's kind of academically gold standard data.
Okay.
And it's like open access, so it's easy to publish methods on it if we want a place to point people. Let me send you a link.
So we won't bother about publication upfront because for that, we have this National Disease Modeling Consortium as well advisory committee council, and we're going to reach out to them for publication policy. We were there in the meeting today morning. Right? So you understand what I'm saying?
Yeah.
So we won't bother about publication upfront. I mean, I'm sure it'll follow, right? You do good work, it'll get published. So
Yeah.
I'm very confident about that. If we really want to, the second thing we want to do, right? One is if we can get access to this.
Yeah.
Second is communicating this in a language that can be implemented. And thankfully, we have the National Disease Modeling Consortium. So if we go back to our municipal corporation, they would probably not listen to us. But if it comes from the health secretary or the ICMR,
It's different.
right? And so if we can target to get this in their ears by maybe 10 days from now, that's the reason I'm in a rush. We're
Yeah.
gonna have the first meeting and we make a case saying that please give us
Okay.
help influence policies, right? Help influence somewhere. At least make recommendations.
Yeah.
And if the recommendations come from them based on the transmission models,
Yeah.
which they can comprehend, maybe prediction model to some extent, then we can actually see a tangible change at the ground because measles, there's an outbreak and we would like to do something to curb it.
Yeah.
Can we do interesting, interesting testing on the what's it called the clinically compatible cases, and really put a break on the outbreak.
Yeah. So a place for you guys, so 10 days is a good timeline for me. I think an email just showed up for you. That's the link to this paper.
You already said that. Great.
And it's maybe something for you to take care of. The paper, I think, is not the most relevant thing.
Okay.
But the GitHub repo is very similar to the type of code that's being used for making these slides. There's just this complexity, which is vaccination, that's incorporated into this code. And that's, of course, a big piece of it. But you might just make sure the GitHub is open to you. It should be.
Are you able to open it?
Piyush Subhash Savar.
22 and
You're able to access it, right?
Right. So I would say and then I'm still on India time for the next week. So if
Are
you,
you be
I'm in Delhi.
Delhi.
So if we need to schedule another call, I can do a more in-depth kind of walk through this code. And probably it will need to be, I'm going to Lucknow for like the visit the middle of the week. So early in the week or late in the week is better. We can figure out timing, but this paper is maybe worth the quick skim. I don't know if it's the most relevant thing for you immediately, but it's like shows you will orient you to the way the code works for sure. And then the code is in the GitHub repo.
Great.
First, archive.
Oh, sorry, I don't know why that wasn't clear. Yeah, so there should be an associated repo.
Dynamic measles cases. PDF, right side.
It's
Right,
like the PDF
yeah.
for sure. Yeah, so here's the paper, and then at the bottom of this page is a link to
Oh, it's a single other paper.
Yeah, there's the GitHub. Beautiful. Yeah, so this is a nice place, I think, to begin. It is complementary to what's in the Pakistan papers GitHub repo, which is like an outdated version of the same.
Okay, so we can go with this.
Yeah, I would go with
Something.
this because I'll share with you something a little more up to date. The issue that we're going to run into is like what I share with you is going to be very specific to the Nigeria data. And so it won't actually run. This will run on your computer.
This is wrong.
Yeah, what I share with you in the future will not, because You'll have to adjust it to work with the data. I can't share the data with you, so like it won't actually produce anything, but the code's structured very similarly. It just has some
This is
assets.
documented.
This is a little more documented. I would say like the paper is where you should go. For
Okay, great.
documentation. And so, yeah, let's maybe see how that goes. And then, in the meantime, yeah, I'll prepare like kind of a bundle of the other code for you, specifically this regression model of like clinically compatible cases. But that's like very standard. Like if you guys have done any kind of like Bayesian regression before, whatever way you've done, that's the same.
And we're happy to explore further.
Yeah,
That's my forte.
that stuff is very simple, actually, relatively speaking, in terms of like the code. Probably there's better code than what I have because I didn't leverage like NMR or any of these like software packages that are better than what I have. So it's worth noting that like don't get too attached to my code. Yeah.
I think where we benefit from what you've done is closing the loop to begin with. We can keep pushing the frontiers.
Right.
I mean, sharpen the saw, but currently we landed up defining wrong problems. We don't want to do that again.
Yeah.
Okay.
Yeah.
It is the wasting
Close
of
the
time.
loop well, we can
Yeah.
fidelity later on.
Yeah, just be in high communication with me.
Yeah.
We can make sure that like I'll tell you also the kinds of measles things that we're doing, and I think it'll be a good way for it to be like a technical and collaborative relationship. And then like as far as like if you guys are wanting me to look at the data directly, I'm happy to do that. It's only
We're happy to share.
okay. It's like that's totally up to you guys, and
We're happy to share with you. And
Yeah,
any insights you can provide asynchronously would
great.
be welcome as well.
Yeah, so we can try to see how that goes and go from there.
Great.
Yeah, but this was great. I'm glad to meet all of you guys. And I'm sorry we didn't get to this your work, but maybe we can schedule something remotely because I would love to hear more about. I think like we've explored a lot of synthetic data type stuff as well, and I think we could do a lot more in that space. So,
Yes, I think this is the beginning. We'll have more.
Yeah, great.
More to speak. Great. I think you need to leave. Sure.
Oh yeah.
Expect your next meeting. 6 minutes to.
Yeah.
Oh, you just closed it.
Oh yeah.
Buy or whatever.
Make sure you delete